Your software design patterns are the key to building reliable AI agents. I wanted to make this video to show you how agentic AI patterns are direct extensions of the classic software design principles you already use every day. Because, as you know, in the end, an AI agent is a software system that uses an LLM as the reasoning engine. It combines that engine with three key things. First, memory to recall past interactions. Second is tools to interact with the outside world. And third is a goal to drive its interactions autonomously. And this is a major shift from traditional programming, and the stakes for ignoring what we have learned about building software systems in the past are very, very high. Without a solid design patterns, AI applications become brittle, unpredictable, and impossible to debug. You can end up with the mess of prompt change and API calls that could fail silently. So, in this video, you will learn first, why classic design patterns are the perfect bridge to think about AI agents. Second, the three foundational agentic patterns: reflection, tool use, and planning, and how to combine these into multi-agent systems using delegation and collaboration. And finally, how to manage, debug, and deploy agents safely with AgentOps. And by the end of this video, you will have a practical framework for designing and building robust AI agents using the engineering skills that I'm sure you already have. So, let's dive in. In AI agentic systems, the fundamental shift is in the control flow. In object-oriented programming, an object encapsulates states and behavior. It has data and it has methods that operate on that data. And you, the programmer, write the control flow. You decide which methods to call and in which order to achieve a goal. Now, let's think about an AI agent. An agent also encapsulates states and behavior. The state is the memory. It is the context window. Its behavior is the set of tools that it uses. But there is a critical difference. The agent has a goal. Instead of you writing code to call method A, then method B, you give the agent a high-level objective, and it decides which tools to use, in which order, to achieve that goal. This moves the complexity from explicit control flow in your code to the reasoning process of the language model. I have seen some developers trying to control AI with complex brittle prompts engineering techniques. The better approach is to give it well-defined tools and a clear goal. Then let the LLM actually reason about it. Imagine a billing service object in a traditional system. It might have a method called charge customer that receives two parameters, the customer ID and the amount. Your code is responsible for figuring out the customer ID and the amount, and then explicitly calling that method. Now, imagine a billing agent. You give it the goal, something like, okay, let's process these month invoices. And the agent, using its reasoning capabilities, might first decide to use a method like, for example, get overdue invoices tool from the list. It then loops through each invoice, uses a get customer detail tool, and finally calls the charge customer tool with the correct parameters. It writes its control flow. The pattern here is moving from imperative commands, like we have in traditional programming, that is like, okay, do this, to declarative goal. Something like, okay, achieve this outcome. Now, pause for a second and think about a class you have written recently. What if instead of calling its methods, you just gave it a high-level goal? How would that change its design? This mental model is the bridge, An agent is a supercharged object that can orchestrate its own methods to achieve a purpose. And understanding this is the first step to designing robust agentic systems. Okay, so once you see an agent as an object with a goal, we can look at the patterns that make up its brain. There are three foundational patterns that appear in almost every agentic system: tool use, reflection, and planning. Let's start with tool use, often implemented with something like function calling. This is the agent's API to the world. It is how the agent moves from just talking to actually doing things. A common misconception is that the LLM executes code, but it doesn't. The language model generates a structured JSON that says, I want to call this function with these specific algorithms. Your application's code receives this other JSON, executes your actual safe native code, and passes the result back to the LLM as text. For example, you ask a travel agent something like, what's the weather like in Lisbon? And then the LLM, which has no real-time world access, knows that it needs external information. It has then a tool called getWeather, so the output will be a JSON like, okay, tool name gets weather, arguments, location equal Lisbon, and then your code sees this, calls your weather API, it gets back something like 25 degrees Celsius and sunny, or something like that, and feeds that string back into the agent's context. The agent then formulates its final answer. That's tool use. It is the agent's hands. Next is reflection, the agent's self-criticism loop. A single pass from an LLM is often flawed. The reflection pattern has an agent generate a response that feeds that response back into itself or another agent for critique. The critique prompt is key. For example, here is a request and the response. Criticize it based on this criteria. It is accurate. Does it fully address the goal? Suggest a specific improvement. The agent then rewrites its initial output based on that critique. For example, a making copy agent writes a product description. It then passes the draft to a critique agent, which responds. The description is factually correct, but the call to action is weak. The original agent takes this feedback and does a second pass, producing a much better result. It is an automated QA loop. Finally, we have planning. If tool use is the agent's hands and reflection is its quality check, planning is its brain's executive function. Instead of reacting instantly, a planning agent first breaks a complex problem down into steps. A powerful pattern for this is REACT, which stands for reason and act. For each step, the agent generates a thought, an action, and wait for an observation. Imagine the goal, something like this. Who was the lead actor in the movie directed by the person who directed Inception? And what is their age? A REACT agent process would look like this. First, so, something like, okay, I need to find who directed Inception. Then the action, it calls a function like a search web with a query like the director of Inception. And then you have observation, something like Christopher Nolan. And then it executes the so. Now I need to find the lead actor of a movie he directed. The Dark Knight is a well-known example. And then an action, again, it searches the web with the query, okay, lead actor in the Dark Knight. And then they have the observation, Christian Bale. And then it goes through the thinking again. Finally, I need to find Christian Bale's age, something like that. And then the action again. Then we search with the query. When it says, okay, Christian Bale age. And then it observes, okay, he has 50 years old. and then it executes another thinking step, and it says, okay, I have all the components, I can now form the final answer. As you saw, this planning makes agents powerful, but also dangerously unpredictable. Let me show you how to manage this unpredictability now, using something called AgentOps. Okay, by now we have built a single smart agent using tools, reflection, and planning. Most tutorials stop here for what I have seen, but this is where the real leverage begins, and where most projects fail if not designed correctly. The real power comes from composing multiple specialized agents into a single pattern, and this multi-agent design, mirroring classic designs patterns like microservices, is a very important skill for AI engineering. The first multi-agent pattern is delegation. Here, a single coordinator or manager agent understands a complex user request. It breaks it down into smaller sub-tasks and delegates them to specialized agents. This coordinator is the single brain of the operation, and because you only want one, it functions much like a singleton pattern for the gang of four, ensuring one central point of control. Frameworks like Crew AI are built on this principle. Imagine a system to create a market analysis report. The user gives a high-level goal like, okay, analyze the market for eVTOL aircrafts. The manager agent then receives this. It doesn't do research. Instead, it defines a plan. For example, first, as a data researcher agent to gather raw data. Second, pass that data to a data analysis agent to identify trends. And third, give the structured analysis to a report write agent to synthesize a document. The manager just orchestrates information flows. This is powerful because each agent can be optimized for its specific task. It is a separation of concerns for AI. The second major pattern is collaboration, which works like an assembly line. Agents work in a predefined sequence where the output of one becomes the direct input for the next. The MetaGPT framework simulates a virtual software company this way. A product manager agent creates requirements, passes them to an architect agent for design, who passes that to an engineer agent. Each step builds on the past. As you can imagine, this pattern is less flexible, but far easier to debug. And choosing between delegation and collaboration is a classic architectural trade-off. As you know, there is no silver bullet. Delegation gives you flexibility, but is harder to control. On the other hand, collaboration gives you predictability, but it is more rigid. The right pattern depends on the problem you are solving, of course. So we have designed this powerful multi-agentic system, but this creates an urgent problem. How do we test and debug them? Well, agentic systems are not deterministic, as you know. Running the same agent with the same goal twice might produce two different plans. And without proper tooling, you get chaos. Imagine an agent stuck in a loop that swamps an API 1,000 times, costing you real money. I have seen this many times. Or one that incorrectly books a non-refundable flight to the wrong city. You cannot just attach a debugger and step through the code, because the code is the model's reasoning process. And this is where a new discipline called Agentic Ops comes in. It is DevOps for AI agents, of course. The core idea is observability. You need to log everything, not just the final output, but the entire chain of those. For every step an agent takes, you must capture the agent's internal thoughts, the specific tool it chooses, the exact argument it passes, the raw output it goes back, and the final response it generated. And this gives you a complete trace of the agent reasoning. And by the way, I really like Lan Smith from the LangChain. He has a very nice web application that is worth it to check out. And you know, when an agent fails, you can look at the trace and see the exact point of failure. Maybe the trace shows something like, okay, the agent first thought something like, okay, I need to find the flight. And then it produce an action like, okay, search flights from New York City to San Francisco, you know, with the date tomorrow. And then there was an observation, something like, okay, API error, invalid date format, please use this date formatting instead. And then the agent saw again, okay, the API failed, I will stop. And this kind of trace is what you really need to understand what was going on behind the scene. And without it, you will just know that it fails. With the trace, you know exactly why. The agent failed to recover from the error. Observability is therefore non-negotiable for production agents. Beyond observability, AgentOps includes guardrails, which are very, very important. And these are safety mechanisms you build around the agent. This can be as simple as setting a maximum number of steps requiring human approval for critical actions like charging a credit card, for example, or restricting which tool an agent can access, or even validating an agent's output before showing it to a user. And building an agent without AgentOps is, in my opinion, like deploying a web service without logging, monitoring, or security. It is a recipe for disaster. So make sure you learn it and use it. So let's pull all this together. We have seen that AI agents are not magic. They are logical evolution of a software design principle you have already been using for your entire career as a software developer. We started with the core idea, like an agent is simple an object with a goal. And from there, we unpacked the three foundational patterns: tool use for action, reflection for quality, and planning for strategy. We then scaled it up, composing single agents into multi-agent systems using delegation for feasibility and collaboration for predictability. And finally, we faced the operational reality that these dynamic systems require a new discipline called AgentOps to ensure that they are observable, reliable, and safe. And these patterns are your new toolkit. Your next step is simple. Don't try to build a complex multi-agentic systems tomorrow. Instead, pick one small, repetitive task you do every week. Maybe it is summarizing a document or creating a pull request description from a commit message, for example, something that I am thinking about it right now. And in the next 7 days, just sketch out a single agent to automate it. Think about what is its single clear goal, what is the one tool it would need. You don't even have to write the code, just design the pattern, and this will make these concepts concrete. And if this way of thinking about AI engineering was helpful to you, subscribe for the channel for more deep dives into building practical and robust AI systems. Thank you for watching, and see you in the next one. Bye.